I just wanted to mention for people that are trying to sort of get a very, very deep understanding of our product. I'm going to keep doing these tech talks. They're all sort of going to be overviews of topics. It's not going to give a super deep understanding of things. There's the tech briefing on our website, which goes into some level of detail, and then there's the other videos. The only thing that we're not going to show, which is I think what some people want to see, is a lecture series of me going through actual diagrams and simulations and a video of me like taking apart one of our collectors or something like that. There are, even though we're trying to be as open with all of our technology as we can, and we're trying to make everything open source and show everything that we can, there are still some things that are intellectual property concerns for the time being. I'm hoping that will change pretty soon. There should be enough information out there to get a pretty good overview of how everything works. I get constant complaints from our partners and our lawyers about putting too much information out. Today I'm going to be talking about, in any sort of power system, but I guess particularly in a solar power system, choosing your base form of energy. All the energy that your system is getting is in the form of light. A lot of that light is visible, some of it's not, but it's all light. And you need to do something with that energy. You need to heat up a room or power a computer, whatever it might be, move something, power anything, right? Cool down your refrigerator, things like this. These ultimate use cases are in many different forms: motion, thermal, electricity. There's really no one form of energy that is overwhelmingly what's used. Heat is the most used form of energy, particularly in commercial and residential applications. You need to be able to have many forms of energy. But the decision that you need to make is sort of, how are you going to get there from this light? You can say that we're not designing a complete power system, which is what a lot of people do, and we're just trying to address a couple of these concerns. So for example, we're going to make a solar thermal collector that just makes hot water for someone's house. Or we're going to design a solar thermal collector, but it's going to be very, very high temperature heat, and it's only converted to electricity and put onto the grid. The reason why electricity became so popular is because electricity is, in an abstract, to use an abstract term, it's a very high quality energy. And the quality of energy thing ultimately comes down to entropy. In general, electricity is very low entropy. And that's good, because there's more things you can do directly with that energy, but it's bad because you always have a lower efficiency when you're trying to make lower entropy energy or higher quality energy. The major benefit of heat that you can't look past is it has a extremely easy to vary entropy. It can go anywhere from the lowest quality dirt energy that there is, and it's generally considered a waste form of energy. You can make it with 100% efficiency to a very, very high quality of energy, and the only thing you have to do to vary that is raise the temperature relative to the environment. And the reason why that's really good is you can make this very low quality of energy at an extremely high efficiency. And a lot of the energy that we use doesn't need to be high quality. So you can heat your swimming pool, you can heat your home, you can power all these sort of industrial tasks where you're just boiling water or something like that, purifying water. You can do with very low quality of energy. And then there's some medium quality of energy things like cooling down your refrigerator, some other things like this. Only after you've powered everything else, by directly using this lower quality of energy, do you increase the temperature of the heat that your system is making, and then convert to electricity or whatever else you're doing and use that higher quality of energy. So the really important thing is you only take that efficiency hit when it's absolutely necessary. What we're doing at Tenkiv is making a complete integrated solar power system that's supposed to be able to power anything. It's supposed to be effortlessly adaptable to fit in all of these different situations. Obviously, what we're making isn't the first solar thermal power system ever, although not really many people have delved into an integrated power system that is based around heat, but certainly not the first solar thermal collector. What is normally done with solar thermal right now is, like I was alluding to earlier, you either target only making very low quality energy and just using it for space heating, water heating, things like this, or you target only very high quality energy, essentially what you do is you have a concentrating collector that only converts to electricity all the time. So heat is this sort of medium, but that heat is just immediately being converted to electricity. And I think, to clarify, something that a lot of people don't realize is heat is used in energy systems all the time. And in most ways of thinking about it, energy revolves around heat. For example, nuclear power or fossil fuels, those are both thermal systems. They burn the fossil fuels, they have a substance undergo fission or fusion and get heat from that. Then they run that heat through a heat engine that produces electricity. One of the things that makes thermal systems in general, but particularly in our case, interesting and I think is an advantage, is that the core problem that you're trying to solve when you're using heat as your medium is just moving the heat around and storing it with as little losses as possible. Because you can always convert from anything to heat with 100% efficiency. So, and this ties into everything else I've been saying perfectly. With electricity, for example, with a photovoltaic panel, all of the effort goes into making that initial conversion as efficient as possible. And you take these huge losses just right off the bat. You immediately are running at very low efficiency, maybe up to 20% or so. Whereas with a solar thermal collector, that initial conversion is 100% efficient. Going from light to heat is 100% efficient. The problem is, as you get into these higher temperatures corresponding to a higher quality of energy, you start losing heat very fast, or you can. Your only job is to make sure that once you have that heat, you don't lose it and you get it where it needs to go with minimal losses. Then separately, when you're trying to power all these different things, that's when you get into the conversion, and you need to maximize the efficiency of those conversions. So when you're using heat to cool something down, essentially you're using heat as a heat pump, like an air conditioner. That is a conversion that has an efficiency associated with it, or when you're converting heat to electricity. And those conversions, by the way, just have the exact same quality of energy entropy issues that we're talking about before. So if you want to get a higher efficiency out of those conversions, you need to lower the entropy of your heat. You need to increase its temperature relative to the environment that you're in, or have a cold side, and then you have a higher efficiency for those conversions. But again, just from a systems perspective, with the actual acquisition of that core energy form that you're using for everything, your issue is just keeping that heat inside of your system, whether it's in transit or storage or collection, always keeping it inside your system and not losing it. But the conversion aspect itself is essentially always 100% efficient, excluding, of course, there's little things that I don't want to get called out for, like, the main thing is so-called optical efficiency. That's not the conversion from light to heat where you're losing energy, and this isn't different than any other form of collecting solar energy, but you do have some reflection off of your cover or whatever surface the light is hitting. And you do have, what's usually factored into efficiency in solar collectors is if your collector surface is a roof, for example, and that roof is 10 square meters, and it's completely covered in panels, but the absorber area is only 5 square meters, then right off the bat, your optical efficiency is going to be less than 50%, because it's usually factored in what percentage of the area that's taken up by your collectors is absorber surface. And this is another thing that we've optimized so that our collector ends up being more efficient at zero temperature differential, which at that point you're just looking at optical efficiency, than even collectors that are meant only to run at extremely low temperature differentials, that are basically just a black sheet of something. So yeah, that's sort of a brief overview of argument of heat versus electricity as your sort of base form of energy that a power system revolves around. Hopefully I gave some explanation of the advantages of using thermal energy as your sort of base form of energy for your system versus electricity. So converting directly from light to heat and then doing something with that heat, as opposed to converting directly from light to electricity and then doing something with that electricity. And I think I'm sort of rambling now and going over the same things I've already talked about. This is Arya's punishment for making me do a video, and I'm really, really tired. So yeah, hope this made some sense to somebody, and I'll see you guys in the next video.